explore a way to estimate the convergence to the stationary measure of a Markov chain, which is called the coupling method. Okay. So let me just remind you that one of the formulas that we have for the total variation distance between two measures is the infimum over all couplings of the probability outside the diagonal. Okay, so that was one of the formulas on the Kantorovich-Rubinstein duality. And remember that a coupling is a measure, is a probability measure on the product space. Okay, so in omega cross omega, such that the first marginal is mu and the second marginal is nu. Okay, so this is a definition of coupling, and we have this formula for the total variation distance between two different measures. So one possible way to estimate the total variation distance between the law of a Markov chain at time t and the stationary measure of the Markov chain is to find a coupling between these two measures. Okay, so there is a definition. Okay, so the definition is the following. Is what we call Markovian coupling. Okay, so what is a Markovian coupling? So what we are going to call Markovian. So the rigorous definition, it's a little bit strange, but then I will explain the intuition behind the definition, and we'll see that it's very easy to construct Markovian couplings. So let me see, I need a new letter, maybe I'm going to call it Q. So let me give you an example of a Markovian coupling so we can understand what is this thing about. So let's take the circle, the random walk on the circle. Okay, so and we take 2 points x and y. And what I want to do is I want to construct simultaneously two copies of the Markov chain, one of the random walk on the circle. So this is the circle. Let us say that the random walk is lazy, okay? Because that's going to be important at some point. So we have xd, yt. Okay, I want to construct two copies of this Markov chain simultaneously. Okay, so imagine that you are running an algorithm and you want to construct both at the same time. So how can we do that? Okay, there are various ways in which one can do that. Okay. So you throw your coin. Heads, tails. And so first, let's think about the case on which this random walk is not lazy. So you throw a coin, and what happens is that this guy jumps here, for example. Okay? And now, in parallel, I want to construct also the random walk starting from y. There are various things I can do. There's not a unique way to do this. One possible way to do it is that you just copy the jump. Since the probability is 1/2, 1/2 here, the probability is also 1/2, 1/2 here. And the result here is also Markov chain, divided on the product space, no? The product of two circles. One circle for the first coordinate xt, and one circle for the second coordinate yt. So this is a coupling. This is a possible coupling. Okay? So if you call xit these are IID random variables with distribution Bernoulli of parameter, let's say 1/2. Okay, we know that we can define the simple random walk like this, right? So at each step, I add this Bernoulli. This is Bernoulli's, but this is Bernoulli's with values +1, -1. Okay. You just add. You take the current value of the Markov chain, and you add +1 or -1. And how do you decide if you add plus or -1? You throw a coin. Bernoulli 1/2. Same probability for both, and you do it. At random. Okay, so this defines xt. So this is an algorithmic way to define xt. You can do the same for yt. So let's say one possibility. Well, we use the same randomness and this defines now a couple xt, yt. And these two guys, they go around together. Okay. Notice that the distance is constant between these two guys. No, they move in a synchronous way. This is one possibility. Another possibility, another thing one can do that probably is more fun, one can do this, right? Because this, if I subtract instead of adding from yt, I'm also going to the left or to the right with probability 1/2, 1/2. Okay? So this is another possibility. Okay? And probably this is more fun, no? Because what you can see from this here is that if we do this, what happens is that the distance between x and y, it goes down by 2 or goes up by 2 at each step with probability 1/2, 1/2. So the difference is actually a random walk. A simple random walk, but a little bit bigger, no? Because it's, the size of the jumps are 2. Okay? There is a third possibility, which is very common in the literature. You can do this, where psi t prime is also a ID with lower nully 1/2, but these guys are independent of the previous sequence. Okay? So if we think about this algorithmically, what we're doing is that in our simulation of this couple here, we're throwing a coin twice. Once for the first coordinate, once for the second coordinate. We're allowed to do that, okay? We can do whatever we want. The only restriction is that it has to be a simulation. It has to be an algorithm, okay? Whatever algorithm we do, and if you forget about the second coordinate, the first coordinate has to be a random walk. If you forget about the first coordinate, the second coordinate has to be a random walk. Then these two guys can have the dependence, whatever dependence they have, it doesn't matter. Okay? So you see that if you do this in this algorithmic way, you always get a Markov chain, right? Because any stochastic algorithm of these forms here produces a Markov chain. So we want, okay, so let's see what does it mean that the coupling is Markovian. So this matrix here, Q, lives in omega cross omega, okay? So it actually has 4 parameters, no? I mean, it's a function of 4 variables, no? Before there was x and y, but now there are x, y, x prime, y prime. Okay, so we want that with respect to the first coordinate, what we see is a Markov chain. So we want the following. So this is the transition rate between these 2 points, these two coordinates on the product space. And we want to say is that if we only look at the first coordinate, the probability has to be the probability of the original transition matrix. So this has to be equal to P x prime. Okay? But this doesn't make any sense, no? Because if this is true for every y and y prime, it means that this Q is constant in y and y prime. Okay? So the secret is that we can add over all y prime here. And what we want is that, because this is the probability of jumping from here to here, but I want to say that the probability of jumping from here to here is this number here. So we want this. We have the sum over y prime in omega being equal to this for every y in omega. Okay? So this condition here means the first coordinate is a random walk, it's a Markov chain of transition probability P. Okay? And the second condition is the one for the second coordinate. So in other words, what I'm saying is that condition A. So I'm gonna rephrase this in words. Okay. So this is the definition. Okay. So I'm going to rephrase it in words. So the thing is, so in words is the process x t y t such that t belongs to 0 is a Markovian coupling okay, so here is not a process, it's a Markov chain. So we assume that this guy here is a Markov chain, okay, from the beginning. Condition A, this guy here is a Markov chain. And B, this guy here is also a Markov chain. In principle, when we are doing Markovian coupling, in the definition, in this definition here in words, I'm not assuming explicitly that the two coordinates are actually the same Markov chain. They could be different. This is something that sometimes happens. Okay. So this is the definition of a Markovian coupling, and here we did some examples. Então, lá temos três acoplamentos diferentes da mesma cadeia.
Não digo X, T, Y, T.
É a mesma.
É a mesma cadeia.
A mesma cadeia. Podem começar de lugares diferentes. So now there is a proposition. I'm not going to prove it because it's very simple, but a little bit. It's just a verification. So it's the following. So if Q it's a Markovian coupling of P, then Q tilde define as. So we are going to define Q tilde in the following way. Okay, so let me explain you what this what I'm doing here. Okay, so let us imagine that we are looking at this coupling here, B. Okay, let's assume that x and y, the difference between x and y is even. Well, in this case here, doesn't really matter because the chain is a periodic, but let us imagine that the difference is even. Okay, so at some point, if I do this coupling here, xt and yt are going to be equal, right? So they are going to meet because the difference is a simple random walk, and the simple random walk on Z is recurrent. And they're going to meet, if you look at the difference as a random walk, they could be doing loops around, and maybe they meet when the difference is not exactly 0 when you project to Z, but certainly they meet when the difference is 0 when you project to Z. Okay? So it means that at some point they will meet. But when they meet, in the next step, they get separated again, right? Because xt and yt are at the same position, and now I throw my coin, and if xt goes here, then yt goes there, and vice versa. And if ft goes here, then yt goes the opposite way. So when they meet at the next step, they get separated again. But if I run an algorithm, I can put in my simulation of the Markov chain an if condition, no? So if they meet, then they go together afterwards, right? So if I do that, okay, so I can, what I'm doing is, the first time they meet, I switch from B to A. This is something I can implement as a code. It gives rise to a Markov chain because it's a well-defined routine. The Markov chain is a coupling because the two marginals, they still behave like a simple random walk. And I'm actually allowed to do that type of things, okay? because I mean, it's something that I can do, no? It's an algorithm. So this thing that I just told you, no, to switch from B to A, whenever they meet, is what this Q tilde matrix is doing. Okay, so if they are different, they go with whatever algorithm you're using, but the first time they meet, I switch to a new algorithm, which is they go together. They jump together. And if they jump together, both coordinates are Markovian. Okay? So now I'm going to introduce a new definition. So this proposition, I'm not going to prove it. I hope I convinced you that this what I just told you is a proof of this proposition, right? Because what I just told you is how to construct the algorithm that realizes this coupling here. And this is the matrix, so it has to be a well-defined coupling. So, but this proposition you can prove it just because you just have to verify conditions A and B, and you have to also verify that Q tilde defined in this way is still a transition matrix. Okay, also it's still a stochastic matrix. Okay, but that's not difficult. You can do it. So let's go to the next definition, which is the important definition. There is something that is called the coupling time. Okay. So the coupling time is the first time that the two coordinates meet. This is the definition of the coupling time. Okay? And now with this definition, we can actually write down a proposition. Okay, so I'm going to write it as a theorem because it's an important proposition. And the theorem is the following: estimate for the total variation distance. So we are going to call this coupling here successful. Okay, successful because, well, it's one way to call it. So whenever a coupling has this property that when the two coordinates stay together after the first time they meet, we say that the coupling is successful. Actually, what people call successful coupling is one that has this property, but also has the property that this cube tilde here is irreducible, which means that someday they will meet. Because strictly speaking, coupling A that I mentioned before is successful by this definition, because the first time they meet, they go together forever. But actually they never meet if they don't start together. But okay, so this is the theorem. And the proof is very easy, no? Well, it's not very easy. It's very easy after one does an observation or proof. So from the proposition, we can assume so this W log means without loss of generality. Okay, so this is the usual notation, W log. We can assume without loss of generality that Q is successful. Okay, meaning that when they get together, they stay together forever. Now the proof is very easy. Why? Actually, Q to the power T is a coupling between these two probability measures. All right, because what happens, if you think about it, this condition here, the only thing that means is that when you fix the first coordinates, this thing here is a coupling between the rows of the random of P. Okay? So what does it mean? It means that it means the following. So if we look at the first coordinate of Q to X dot, that is it has this law here. It has the law PT. And if you look at the second coordinate of the matrix QT, it has this probability here. So actually this is actually equal, less or equal so maybe I'm going to write that because it's maybe it's the first time you see this argument, so maybe it's not so easy to grasp, but we have that Q T XY dot dot. So what is this? It's the probability of the in the coupled chain to go to some place, given that you start at the first coordinate starts at x and the second coordinate starts at y. So this, as a probability measure, is a probability measure in omega cross omega. And the first coordinate is pt x, and the second coordinate is pt y. So this is a coupling. Between ptx and pty. Therefore, so now we can do some computations. Okay, so what we see is that the total variation distance between these two measures is less or equal than so this is a coupling, so it's the probability of the off diagonal of this. Okay, so it's the sum of xy s prime different from y prime of qt xy x prime y prime. Okay, so is the off diagonal probability of this guy here. Remember that this is successful. So each time they meet, they stay together. So this probability here is decreasing in t. So this is equal. So it's the same thing as the probability in terms of the chain xt. No, is the probability that xt is different from yt. It's exactly the same thing. But if they are different, it means that the coupling time is bigger than t. Because if the coupling time is smaller than t, smaller or equal, then they have to be equal because they stay together. And if they are different, then the coupling time is bigger. Okay, and so we have this estimate. Okay, so we have this estimate for the total variation distance between the law of the chain at time t started at two different points. And now there is another proposition that we can prove, which is similar to this one, which is the following. Now we are going to prove the following estimate. The distance to the stationary measure is less or equal than the maximum over x and y of the probability of this bigger than t. Okay? So strictly speaking, I have to put an x and y here. Okay, because what I'm doing is that I'm starting the Markovian coupling from the initial condition xy. Right? So remember that when we are computing a probability and we want to remind what is the initial condition of the Markov chain, we put it up here. Okay? So this is the proposition. So so let me see. the proof is the following. So I want to estimate pt x dot minus pi dot. Okay? Total variation. So this is the same thing as pt x dot minus the sum over y in omega of delta y dot pi of y. So pi is the invariant measure, okay? So this is the stationary measure of the chain, of the original chain. Okay, so when I write this type of things, remember that when I write dt, it means that I am assuming that my chain is has a unique invariant measure, because otherwise I cannot define the dt. Okay, and the unique invariant measure, I'm calling it pi here, and so pi is this. So this delta y is what? Is the probability measure that puts mass 1 on the point y and mass 0 everywhere else. It's what we call the delta, the Dirac delta, the delta of Dirac at the center at y. Okay? So the delta of Dirac center at y. So remember that the space of probability measures is a convex space. Okay? So every convex combination of probability measures is a probability measure. Being a convex space, so it's a simplex, no? It's like a triangle, but multidimensional. Okay? And a triangle has this property that every point inside the triangle is a convex combination of the 3 vertices of the triangle. So in general, every probability measure on the set omega is a convex combination of the deltas of Dirac, because the deltas of Dirac are precisely the vertices of the simplex, which is just this multidimensional triangle. Okay, so you can always write the invariant measure as a convex combination of the deltas. Here we can use the fact that the total variation norm is a norm to say that this is smaller or equal than the sum of the norms. Okay, I can write this guy here as the sum over y of pi y times pt, because the sum is just I can put this inside the sum, because the weights of the sum add up to 1. So I can write this as this. This is what I wanted to do? No, this is not what I wanted to do. I wanted to do something else. So it's the same argument again, okay? Because pi is invariant. So pi is invariant, it's a stationary measure, and this is just the product of this matrix times pi from the left. So it's equal to pi. So what I wrote here, this is just pi pt of dot, which is equal to pi, because pi is invariant. Okay, so now again, so the total variation norm is a norm, therefore it satisfies the triangle inequality, no? Or Minkowski inequality. And what we have here is ptx dot minus pty dot. and this is smaller or equal than the sum over y of pi y, the probability, and now I use the theorem, no? So it's the probability of the coupling time being bigger than t, starting from x and y. And from here, the proposition follows, because the sum is a weighted sum. The weights add up to 1. Therefore, this sum is smaller than the maximum. I take out the maximum from the sum and get the sum of pi, which is 1. And now I take the maximum over x. That gives me the t, and you get here the maximum over x and y. Okay, so let me just go one more step here to say that this is smaller or equal than the maximum over y of this probability. Okay, and now we take the maximum over x and we obtain what we wanted to get. Okay, so this is a way to estimate the distance to the stationary measure in terms of couplings. In order to do this thing here, I have to couple. I have to be able to couple the chain starting from any two different points. Okay. So now that I have this theorem, I'm going to make an example. Okay. And I'm going to take the lazy random walk on Z n. Okay? So I have here my circle, and I have here, let's say, xt, and here I have yt. Okay? And I want to couple, so they start at, let's say, x and y. And I want to couple these two chains in such a way that in some Markovian way, okay? And the idea is to do it in such a way that they have a good chance to meet, okay? So in my previous notation there, so A was bad, no, because they just move in a synchronous way, they never meet. B was a little bit better because they had a chance to meet. There was a problem with B that maybe if they are at distance, if they are not at an even distance, they never meet. So let's imagine that we use the coupling B. Okay? The work is lazy. So let's say that so when the work decides to stay put, both stay put, and then when they move in opposite directions. Okay, so if this one moves clockwise that way, the other one moves counterclockwise, and vice versa. If they do that, there is a problem, no? Because if they are at distance 1, we have this problem that they are going to cross without coupling. So one way to solve that, which is very ingenious, there are various ways to solve that, no? One way to solve that problem is that when they are close, we see what we do, okay? But there is a very ingenious way to do it, is that is to take our chances to use the laziness of the chain. So what we are going to do is that we are going to do the following algorithm. When one of the chain moves, the other one doesn't move. The probability of moving is 1/2, right? So I can do that. No? When one moves, the other doesn't move. Okay? So I'm going to define two Bernoullis, no? So I'm going to define this guy here. So I'm going to define theta t. Okay, I'm going to define theta and psi. And they are IID. And the law is going to be, let's say, uniform. Okay, let me write it in this way. Okay, uniform in the set 1, 2. Cross minus 1, 1. Okay? What does it mean uniform in the products set? It means that here is Bernoulli 1/2, here is Bernoulli 1/2, and they are independent. It's the same thing, right? Because if both are Bernoulli, if both coordinates are Bernoulli 1/2, then the product measure is uniform. Because actually the Bernoulli 1/2 is the uniform measure on the set of two elements. Okay? Then what we are going to do is that we are going to define xt it's equal to plus 1, no? xt if theta t is equal to 2 and xt plus psi t if theta t is equal to 1. Okay, so the coordinate theta tells me which coordinate on the coupling will move. And then yt is the opposite thing, right? So it's going to be yt if theta t is equal to 1 and yt plus psi t if theta t is equal to 2. Okay? As you can see from this construction, the usual way in which we do Markovian couplings is actually explaining how to do the coupling as an algorithm, okay? So we give an algorithm of how to construct the coupling. We don't write matrices, no? Nobody wants to write down matrices, it's too complicated. And this is an algorithm, and actually it's very easy to see that this is effectively a Markov chain, right? Because as you can see, so how does it work, this Markov chain? It's okay, so the next step on this stochastic process is a deterministic function of the previous step and the randomness that I'm selecting at that step. So at each step, I do some random draws of some numbers that I'm going to use. Once I drew these numbers, I use these numbers deterministically to decide what the chain is going to do. Okay? So it's just a random algorithm. So Markov chains and random algorithms are exactly the same thing. So in particular, this is a Markovian coupling of something. And of what? Well, one can check that here what happens is that this random walk is just a simple random walk, no? 1/2, 1/2. It's lazy, no? It's lazy because the probability of this is 1/2. And given and the probability of moving is 1/2, and then you move to the left or to the right with probabilities with the same probability.
When you get to theta 2, you don't get out of theta 2.
Huh?
If x equal 2, you don't get out of 2 anymore.
No, it's not x here, it's theta.
Okay.
So you
Just repeat the
okay, so you just draw at this step. So your random algorithm has 2 steps, no? First you throw a coin and you decide which coordinate is going to move. And then you throw another coin and you decide where to move the corresponding coordinate. So this is a Markovian coupling. Okay? And what you can see what happens with the difference between these two guys? So the difference goes up and down by 1 with probability 1/2. Right? Because with probability 1/2, one of them stays at the same position and the other one moves. It could move away or in the direction of the other guy. So we observe that xt minus t yt is a symmetric random walk, not lazy, on Zn, and so what happens with this chain is actually, so you start here somewhere, at this point here, which is x minus y. And whenever you arrive to 0 or to n, the chains are coupled. Because they can couple because they go together, no? So here they can couple because they go this way, plus, or because they go the other way around, and they couple because one of them catches up the other one, no? Given one cycle around the circle. Okay? So I'm going to write it like this. So tau xy so we see that this coupling time, it's equal in law to the heating time of the strings of the interval on the simple symmetric random walk. Okay? Strictly speaking, it's not the same thing, right? Because this difference is not a random walk on Z. It's a random walk on the circle, right? But in law, it's exactly the same thing because we have a mapping. No? We can make a bijection. No? We can do the the formal way to do it is that you use the universal cover. Okay, so there is something called the universal cover. That is a function that goes from the circle to Z, but it's not. It doesn't really go from the cycle to z. So what is happening is that there is a function that you can take a function that goes from z to the circles and goes around. And then there is a unique way to invert that function for trajectories that only takes nearest neighbor jumps. Okay, so, and for this one, we know the probability. No? We already computed. No? So what do we know? We know that the probability of the n bigger than t was less or equal than. So we did this computation. It was exactly. So it was the expectation of this heating time here, no? Divided by t. And this one, exactly. Well, that was the Gambler's ruin, and this is was x minus y, n minus x minus y, divided by t. And now we maximize over x and y. And this one is maximum for n divided by 2, so we get n squared divided by 40. Okay? So what we just proved is that the distance to the stationary measure for the random walk, simple random walk, is less or equal than n squared divided by 40. So you can compare this with the computation we did last time. Okay, so it was on Friday or on Thursday, I don't remember. I think it was on Friday. We estimate this thing for the simple random walk using Fourier analysis. We use Fourier series. In the case was discrete Fourier series. How is it called that? FFT. To compute this distance more or less exactly. And we showed that d n squared t converges to some function. So if you put here t equals n squared, what we get is 1 over 4t. Okay? So it's not in contradiction with what we did last time. And that is actually up to a constant is a sharp bound. Because we actually show that this number converges when you replace t by n squared t. So let me put it in this way. So we show that this number converges to some function. And here we're proving that that function is smaller than another function. So in terms of n, this inequality here is sharp. It's best possible, except for a constant. The constant depends on t. And maybe the constant in t is not that good. We know that it's not that good because we know that this guy here decays exponentially to 0 as a function of t. And this one does not decay exponentially to 0. But this is just because we computed only the expected value of the heating time. It is possible actually to compute the exponential moments of that heating time. Using exponential moments of the heating time, the Markov inequality will give an exponential bound here. So this bound is not bad. And in particular, it gives the right answer. Okay? So let me do another example. Okay, before entering into this example, an observation, okay? This coupling here actually also works if the walk is not symmetric. I could have defined it here, no, instead of taking uniform in the second coordinate, here I could have taken probabilities P and Q for minus and plus 1. And what happened is that the difference is still a symmetric random walk, right? Because what happens is that you have to be a little bit more careful to see which one is which. But the point is that if the guys are in this position, this guy goes in this direction with probability P, and this guy goes in the opposite direction with probability Q. Therefore, the probability of the jump going in the right direction is P plus Q, which is 1. Okay, well, divided by 2, no, because you have to do the computation, because it was not P and Q, it was P and Q divided by 2, no, because it's lazy. So the probability is 1/2. It's P plus Q divided by 2. The probability of going in the right direction. Going in the opposite direction is also, this one goes that way is Q, this one goes in the other direction. So the point is that they get closer because one of the chains they did a clockwise jump, or because the other chain did a counterclockwise jump. Therefore, the asymmetry cancel, and you get still a symmetric random walk. Okay?
Aquele último passo ali, então, só para confirmar, o n ao quadrado sobre 4t é um resultado conhecido da última aula, né? Esse passo.
Não.
Ou isso é um...
É o teorema que está lá.
Não, sinceramente não entendi por que o n é quadrado sobre 4t.
Aqui é a cota que a gente tem.
Que foi o resultado da última aula, que já era conhecido, né?
Isso aqui já é.
Então tá. Era isso que eu queria saber.
E agora a gente pega aí o supre e a gente obtém o
Eu
D.
tô pensando que pudesse ser algo como Chebyshev, porque parece um pouco, mas não é, né?
Daqui para cá é Markov.
Markov, mas a última.
A última é maximizar. Eu tenho uma função, a função x n menos x, que eu calcular o máximo dela. E o máximo é para n sobre 2. So it works actually for the asymmetric case. Now, let's see what happens if one tries to do the same thing for, instead of the circle, the periodic square. Okay? So we have the square here. Well, I don't know if you observed that, but I have a very particular way to draw lattices and intervals, no? which is by bisection. So usually people, what they do, no, is that they do this, no? And then you have this problem that the last one is small. But then you try to solve it, no? Okay, the last one, let's do it like that. But then these two guys are smaller. Okay? It turns out that when you draw an interval by bisection, most of the intervals don't have the same size, but visually they look the same. Okay, so if you start to look at it, you will see that this one is probably the smallest and this one is the largest. But this is not so evident here, but it's more evident here. Okay, if you try to draw a lattice not by bisection, but what people usually do, if you do this, it looks bad, no? Because the last one is too small, then they are all rectangular. No, not so nice. But if you do it by bisection, it looks nice even if the lines are not really straight. For some reason, the eye likes random imperfections. Yeah, so in physics, they say sometimes, no, that crystals, they have symmetries, no, because the atoms are arranged in these periodic things, and there is a classification of all possible symmetries that you can have in a crystal. No, there are a finite number of them. But the most symmetric solid is not the crystal; it's the amorphous solid. So in the amorphous solid, there is no crystalline structure. The atoms are just put there in some random way. And since they are put in some random way, they have all the group of symmetries is continuous. Because whatever motion you do of something on which the atoms are arranged in a random IID way, they're still in a random IID way. And so, glass. Glass is amorphous. No, not glass. Let me think. Yeah, glass. Yeah. This crystal and glass are not the same. No, crystals are crystalline, no, but glass is amorphous. So glass has more symmetries. So you can make a ball, a spherical ball of glass, and that's perfectly spherical. And if you throw a light, the light goes in the right way, in no matter which direction. So in particular, so this is a nice way to draw a lattice. So here, we have 2 points here, and we want to couple these two let's say lazy symmetric random walks in such a way that they meet, okay, with a good probability. Because we want to estimate the distance to the stationary state. And of course, if our coupling is bad, the estimate that we're going to get is bad. Okay? So something which is known is that in dimension 3 and higher, the simple symmetric random walk is transient. So what does it mean it's transient? It means that it has a positive probability of never coming back to the origin, to the position where it started from. Okay? In dimension 2 is not transient, but the probability of coming back is logarithmic small. So it means that you have to wait times of size exponential in order to see the random walk coming back to the origin. So it's not a very good idea to try to do the same coupling. So we have to do something different, okay? Because if we just do the same coupling that we did there, so how would this coupling work there? So we probability 1/2, one of the two moves, and the one that moves follows a standard simple random walk. Right? So if we do that, both coordinates are lazy random walks, and the difference is going to be a standard symmetric random walk. And the difference being a standard symmetric random walk, it means that in dimension 3 they almost never meet. They will meet someday because this state space here is actually finite. So the product space is also finite, and the chain on the product space is irreducible. So they're going to meet someday. But it would take too long. So you have to do something more clever. Okay? So one way to do that is what people call the coordinate by coordinate coupling. So we start doing the same coupling we did there. And we look at the first time, one of the coordinates is the same. At that point, we can freeze that coordinate. We can say, okay, these two coordinates now they move together. And then what we do is that the other ones now they do the same coupling as before, but the one that is frozen, it moves the same. And the other ones, they do whatever they have to do. And then, when a second coordinate is the same, we freeze it too. So we freeze the coordinates one by one. If we do that, what is going to happen is that we have to wait this d times, basically. And so the estimate that we are going to get is d is going to be d times n squared divided by 40. Basically, maybe we will lose an extra constant because we have to do the computation a little bit more carefully, because maybe it's not exactly lazy 1/2, 1/2. There is something there that has to be checked out. But we are going to get something like a function of d times n squared divided by 40. Well, the 40 you can absorb in the constant. So you have the factor n squared divided by t and a function of the dimension. So this is what is going to happen in this situation here. Okay? So you have to do something more clever. So how do we do that, no? So we need to do a coordinate by coordinate coupling. So coordinate by coordinate So how does it work? This coordinate by coordinate coupling. So it goes like this. So at step A, we do like we did there, okay? So we define xt plus 1 is going to be xt if theta t is equal to 1, to 2, and it's going to be xt plus psi t if theta t is equal to 1, and yt is going to be equal to plus 1, yt if theta is equal to 1, and yt plus psi t if theta is equal to 2. Okay? And this psi t here is no longer just plus minus 1 with probability 1/2, no? It's actually a random direction chosen uniformly among the 2D possibilities, okay? So xt, so psi t here. All these random variables, theta and psi, are all independent, and theta t is Bernoulli 1/2. Psi t is uniform among all possible directions. No? These are the canonical vectors, and each canonical vector can have two different directions. So you have 2D possibilities here. Okay. So this is this is step A, no? And now we define tau 1. Which is the first time one of the coordinates meet. Here we have two possibilities. We can do the first time one of the coordinates meet, or the first time the first coordinate meet. One of the coordinates is slightly better than the first coordinate, but not much. Okay? So just because it's easier to write, I'm going to do the first coordinate first. Okay? So the lazy random walk on ZD can be interpreted in two different ways, okay? One way to interpret the lazy random walk on ZD is the following. So with probability 1/2, I don't do anything. And with probability 1/2, I choose one of the 2D possible directions to jump. Okay? That's one interpretation of the lazy random walk on ZD. Another interpretation is, first I choose one direction uniformly at random, and now I'll do a lazy random walk on that direction. So with probability 1/2 stay in my position. When probability 1/4, I'll go to the front. With probability 1/4, I'll go to the back on the direction I just chose. Okay? So these are two possible ways on which one can interpret the lazy random walk on ZD. Okay? So if you wish, if I give you a Markov chain, there are various ways on which you can simulate it. Okay? You can use your randomness in different ways to get the same simulation. One possibility is what I just told you. You first choose a coordinate, and then you do a random walk on the coordinate. or you just directly choose one direction uniformly at random and take this step. From the point of view of simulation, okay, of running time, both things are the same. But sometimes, because of convenience, it's easier to code one of the two. And sometimes you are going to use that simulation for something else, and it's better to use one or the other interpretation depending on what you want to do. Okay? So, for us, it's going to be convenient to think about the second interpretation, that we choose a direction uniformly at random, and then we do random walk. Okay? So, now let's go to step B. That was step A. So, B. Step B. So I'm going to do it inductively, okay? So I'm going to assume that I did I of those steps. So we do the following. B1. First, we choose direction JT. If JT is less or equal than I, then xt plus 1 it's equal to xt plus psi t e JT, where psi t is equal to plus 1 with probability 1/4, 0 with probability 1/2, and minus 1 with probability 1/4. And yt plus 1 is equal to yt plus psi t jt. B3. If jt is bigger than I, then okay, so we choose a direction, so one of the D directions, uniformly at random. If the direction is one on which the walls are already coupled, they jump together. So we maintain these coordinates coupled. If the chosen direction is not one that is not one of the directions that's already coupled, then we do this coupling here. So we throw a coin. One of the chains move. The other one doesn't change. That doesn't move. And the step of the one that is going to move is chosen uniformly at random among the two possible movements in the chosen direction. And then we define t I plus 1 the first time that the next coordinate is coupled. So what can we see from this? Okay, so we see that the coupling time, I'm going to put here a D just to remind us that this guy here is the coupling time in dimension D. Well, is TD minus TD minus 1 plus TD minus 1 minus tau D tau D minus 2 and the last guy is tau 1. Okay? So the coupling time is the sum of the time I need to couple each one of the coordinates. Okay? So I couple the first coordinate. I couple the second coordinate. I couple then, after that, I couple the third coordinate and so on and so forth. Each one of these guys here is one of the coupling times of the one-dimensional. Okay? So these are highly dependent, okay? They are not independent these times, okay? They depend one on the other because they depend one on the other because of the initial condition, okay? Because the first coordinate is coupled. Where now are the second coordinates? The second coordinate is completely random because it takes time to couple the first coordinate, and then the second coordinate now is a random variable. I have two second coordinates, no? One for xt, one for yt, and we don't have any idea where they are. So given the initial positions, these times are independent, but they are not independent because the initial position of each one of those guys depends on how much time it passed after we coupled the previous coordinate. Okay, if the first coordinate is coupled very fast, then the second coordinates are not very far away from the position they started with. But if for some reason the first coordinate took a long time to couple, then the second coordinates are far from the initial position. Okay, so they are not independent, but it doesn't matter. Okay, because we are going to use Markov. When I compute the expectation of the sum is the sum of the expectations no matter what. So this is equal to the expectation of tau d minus tau d minus 1 divided by tau plus the expectation of tau 1 divided by t. This guy here has some random initial condition, but it doesn't matter because actually what we did is what we compute the supremum, the maximum of that expectation. So this expectation starting from somewhere is smaller or equal than the expectation starting from the worst case scenario. So all of these guys are smaller or equal than n squared divided by 4. Okay, so here I'm cheating. I'm doing something wrong. Let me see what is that I'm doing wrong. Okay, so the first coordinate is going to move only if I choose the first coordinate to move. Okay, so that happens with probability 1 over d. Okay, so it means that this time here, each time of these times here are delayed a factor d with respect to the one-dimensional. So when I compute these expectations here, I actually have to factor in that d, because in average here I'm using 1 over I'm taking a step only each 1 over d steps. In principle, this is not true. No, that what I'm doing is that okay, I have this random time that has some expectation, and now I'm saying I'm doing this random time, but only at the random steps, which with probability 1 over d, and I'm saying that the expectation is just the product of the expectation. This is not completely rigorous, but what you can see is that actually these times are independent between them, no? Because the time I have to wait until I do a step on the first coordinate is a geometric of parameter 1 over d. And then the step that I'm going to do is independent of how long I waited until doing the step. Therefore, it is true that that random time t is a concatenation of two independent random times. Okay, so that has a name. No, it's a Wald theorem. So for Wald theorem, the expectation of the new random time is just the product of the expectation. So you get d times the previous expectation. So you get d, so you get d n squared, d squared divided by 4t. Okay, so we get an estimate which is quadratic on the dimension. One comment here. In principle, I could have done it a little bit differently, and it would be faster. So, if instead of waiting until the first coordinate couple, I wait the tau 1 is the first time one of the coordinates couple, you can check that you don't have to wait times of order d. You have to wait less. So you can take that into consideration, but this not if you do that, if you follow that idea very well with all the details and you do it the best you can, you only get a factor 1/2 here extra. So it's not really worth it. There is another coupling that one can do, which is called chain coupling. Chain. Which is different, okay? So chain coupling is the following idea. One can imagine that actually the most convenient way to couple these two random walks is to do it in such a way that if they move in this direction, in the direction perpendicular to the orange line, they move together. And if they move in the direction parallel to the orange line, we do the the one-dimensional coupling. In that way, what is happening is that you are doing one-dimensional coupling. So the coupling time should be the same as the one-dimensional, basically. This can be implemented. I'm not going to do it now. You can think about it at home if you want to. Okay, it's because you see that this is discrete. You cannot move transversal. What does it mean? If I'm doing up and down, left and right, what does it mean to move in this transversal direction here? Okay, you can think about it, and you can define that in some sort of random way. But it is possible to do that, and what happens is that if you do it in the right way, you can come here and slash the square and get a log n, a log d. So d log d. So chain coupling allows you to get an estimate here of the form d log d, which is that's much better than d square. Okay. So the chain coupling is actually people did it in continuous, not in, so chain did it for Brownian motions, not for random walks. I have in some paper I wrote the adaptation for random walks. So if you try to find it, maybe you won't. Especially because the paper was never published with that part of on it. Was removed in edition at some point. But anyway, it is possible to do d log d. This is sort of relevant in some context, okay? Because as I was telling you, and this is going to be the second part of the course, no? Now we're going to enter into Markov chain Monte Carlo, no? Finally. But we have this random walk, and we're estimating the mixing time, no? Estimating d of t is the same thing as estimating the mixing time, no? Because then to compute the epsilon mixing time, you just need to see at which time dt is smaller than epsilon. So from here you can easily compute the mixing time. And if you have a simple random walk on a d-dimensional lattice, there is this dependence on the constant, so the n squared divided by t, it's okay, because it seems that it tells you that at times of order n squared, you are more or less close to the stationary state. But this number here in the dimension is very good, because so the first application that you can do with Monte Carlo is integration. Okay, so how do you do integration? Okay, so you have a solid, and you want to compute the volume of that solid, and what you do is that you do a grid, and then you do a random walk on the grid, and you record how many times you are inside the solid. The proportion of time that you spend inside the solid is going to be an approximation for your integral. And that number should converge when the law of the random walk converges to the stationary state. Because the stationary state is the uniform measure, and then the proportion is going to be just the volume. So that converges in this, it has this n square, no matter the dimension. I mean, for any dimension, this is the dimension. So you see that this number is polynomial in the dimension. It's polynomial in the dimension, polynomial in the discretization. So for very big dimension, that simple method beats quadrature. I mean, quadrature methods that compute the integral via like Runge-Kutta, no? That's the usual name of things. So via approximations of you have the function, you approximate by polynomials, and then you compute the integral as sums of volumes of squares or more sophisticated triangles or whatever. So those methods they have a very good convergence in this number here n, but they are very bad in D. Okay, so the constant here is usually exponential, but so this very simple first Monte Carlo algorithm, which is, so you want to compute the volume of a solid, so you put a grid in, you always have to put it inside a grid, no? This is basic. Now that you have a grid, you do a random walk on the grid, and you count how many steps you are inside the solid, how many steps you are outside the solid, and that's your volume. And that's the simplest Monte Carlo algorithm that one can imagine, and it converges slowly in N, but very fast in D. So that means that these estimates that may look a little bit innocent are not so innocent when you are in what nowadays is called high dimensional probability. When D is very big, what is important here is not the dependence on N, but the dependence on D. And the chain coupling shows that the convergence is faster, is D log D, not D squared. And this is about the proof, okay, of this estimate here. The estimate is about the one random walk, not coupled random walks. Okay, so remember that. So our method gives you some estimate, but this estimate maybe can be improved. But this is still something good enough because it's already polynomial in D. Okay. Okay. So let me stop here. So now yes. So Thursday, second exam, it goes up to Friday. It might have something about coupling, but if I put something about it, I'm going to put all definitions and all the required things on the exam, so you don't have to really study what we did today. Okay? So no. So Friday we don't have a lecture. Yeah, usually the city is too chaotic already on Friday, so it's so usually the previous experience show that on Friday quorum will be very small.